on the top of your notes, you're going to write trigonometric probably Latin. Trigonometric substitution. And this is going to be with integrals involving the square root of a squared minus u squared. So if you remember how these formulas showed up on your yellow sheet, the a was a constant, it was a number, and then the u would be the variable expression, so it might be an x, but it might be something more complicated than that. So square root of a squared minus u squared, square root of a squared plus u squared, and square root of u squared minus a squared. So basically, this is the way of integrating that's the backwards version of what you just did. So we know that if we get an expression that has the square root of stuff like this, that it probably came from an inverse trig function, and it came from drawing those triangles and having your Pythagorean theorem to find your third side, and that's where all those square roots come from. So what we're doing today is we're going to be integrating the type of stuff that we were finding the answer for last week. All right, so the first step is to use the Pythagorean identities. So if we have a squared minus u squared, then the Pythagorean identity that we're going to use is 1 minus sine squared equals cos squared. So the Pythagorean identity itself is actually sine squared plus cos squared equals 1. So this is a variation of that identity. If in the problem we see a squared plus u squared, then we're going to use 1 plus tan squared equals secant squared. And then if we see u squared minus a squared, we're going to use secant squared minus 1 equals tan squared. So what we're doing basically is we're using the square root, whatever that value is, to recognize what trig function it came from. So in the triangle, what would have been labeled. So we're still going to be drawing triangles, we're still going to be dealing with trig functions and all that stuff today. All right, so here is our first example. We are going to integrate 1 over x squared times the square root of 9 minus x squared dx. So my first goal in a problem like this is going to be to take this problem and replace it with trig functions. That's my first goal, okay? So is this the first, second, or third situation? First because a is the number. Okay, so what I'm going to do is I'm going to say I'm taking this part 9 minus x squared, and then I'm going to rewrite this. And I'm going to say 9 minus, and I have to figure out what should go in the parentheses so that I can use 1 minus sine squared. Okay? Now this is a 9, not a 1. So I'm going to want to be able to take out a GCF of 9 once I simplify this problem. So what should I put in here so that I could take out a GCF of 9 eventually? not a 9, because it's squared. I need a 3. So you'll see better in a second why we did that. And then we need it to say 1 minus sine squared, so this is going to be a sine. So that means that my x is going to be replaced with 3 sine theta. X is being replaced with 3 sine theta. All right, so if I keep simplifying this, I'm going to say that's 9 minus 9 times sine squared. So that's if I take 3 sine and multiply it by itself. That gives me 9 sine squared. And then I can go ahead and think of this as taking out the GCF, which gives me 1 minus sine squared. And 1 minus sine squared can be replaced with what? Cos squared. Okay, so now I can finish this. What's the square root of 9 cos squared? 3 cos. Okay, so I have the square root of 9 minus x squared is going to be substituted with 3 cos theta. X is going to be substituted with 3 sine theta. And if I take the derivative of x, what is the derivative of 3 sine theta? 3 cos theta d theta. Okay. So this x right here is going to be replaced with 3 sine theta, and it's x squared, so I'm going to have to multiply it by itself. Right? This expression right here is going to be replaced with 3 cos theta, and then the dx is going to be replaced with 3 cos theta d theta. Okay, so see how everything that was in terms of x I'm replacing with something in terms of a trig function and a theta instead. So I no longer have a variable of x, now I have a variable of theta. I've completely replaced the problem. Okay, so I'm going to go ahead and write down what I have. I have 1 over, my x was 3 sine theta, and that needs to be squared. My square root of 9 minus x squared is 3 cos theta. And then my dx that's being multiplied by this is 3 cos theta d theta. Okay, so now we want to go ahead and simplify what we have. What do you guys see? These can cancel, right? Okay. So I have 1 over, what do I get when I square that stuff on the bottom? Okay. And that 1/9 I can pull to the front. What is 1 over sine squared? Cosecant squared. So I'm going to take the 1/9, I'm going to move it to the front. Okay, and then this is where I have to kind of remember my trig derivatives. One of the trig functions, if you take the derivative of it, it goes to cosecant squared. Anyone know what it is? One of the trig functions, if you take the derivative of it, it goes to cosecant squared. Cosecant squared is the derivative of something. Anyone have their yellow sheet handy? I think you had it. What'd you say? It's cotangent. So the derivative of cotangent is negative cosecant squared. So the antiderivative of positive cosecant squared would be what? Negative cotangent. So I'm going to say this answer is negative 1/9 times cotangent theta plus c. All right? Now, we have found the answer, but our answer is in terms of theta, and we need our answer to be in terms of x. Okay? So what we do is we draw a triangle, and we label the information that we have. All right? Now, you can use this part right here and this part right here. It's going to give you different sides of the same triangle. So sine, if we think about dividing the 3 over, I could say sine is x over 3, right? And so x over 3 would be opposite over hypotenuse. So if this is theta, then opposite over hypotenuse. If I think about this one dividing the 3 over, I would have the square root of 9 minus x squared over 3, which fits because cos is adjacent over hypotenuse. So we have adjacent over hypotenuse. Now, if we look at this triangle, what would cotangent be? Oh, you're thinking, so you can do cos over sine, or you can just do the flipped version of tan. So tan is opposite over adjacent, so cotangent would be adjacent over opposite. And so cotangent is this side over this side. So we're going to keep the negative 1/9, and we're going to multiply that by adjacent over opposite. And then we have our answer. We can just put all of that together. And we have done that integration problem. And we don't necessarily have another way of doing these. Some of these problems you could use U substitution to solve, but the one we just did, you couldn't. So on this one, if you didn't know this method, you would have been stuck. You wouldn't have been able to do this problem.
What if you just split it up as one of the...
You can't, yeah, you can't split it. Okay. Now do a million on your own. Shall we try another one together? Yes? Okay. I'm going to use a brownish sheet. Okay. So on this one, we have dx over square root of 4x squared plus 1. So if we look at those 3 different things, which one does this one fit? The second one. So we're going to be doing 1 plus tan squared equals secant squared, or since we're doing the backwards version, we could say tan squared plus 1. Okay? So I'm going to say square root of 4x squared plus 1 4 times something squared plus 1, and I know that what I'm doing right here is I need this to be tan squared plus 1. Now this is a little different than the last one, right, Leon? On the last one we had a GCF of 9 that could be pulled out. Are we going to be able to pull out a GCF of 4 this time? No, because of the one right here. Okay. So we need to think about what number would go here that would cancel with the 4. 1/2, because 1/2 when it's squared would become 1/4, and then the 1/4 would cancel with the 4. So we're going to say 1/2, and then we know we wanted this to be a tan. So over here I'm going to say my x is 1/2 tan theta. And then I can go ahead and go through my simplifying. So I've got 4 times 1/4 tan squared theta plus 1. And so the 4 and the 1/4 cancel. And I just have tan squared theta plus 1. And tan squared plus 1 equals secant squared. And the square root of secant squared is secant. Okay, so this is one substitution that we have. Then we also have that the square root of 4x squared plus 1 equals secant squared. That's the second substitution we have. And then what's the third one that we have to find? Dx. So derivative of x is dx. What's the derivative of 1/2 times tan? 1/2 secant squared, and then we make sure we got our d theta. Alright, so on this one, we don't have a plane x in the problem this time, so we don't really have to use this one. But we do have a dx. So we are going to replace the dx. And then we do have the square root, so we are going to replace that as well. So now we have 1/2 secant squared d theta divided by secant theta. Okay, so what do we get? Yeah, and then secant cancels with one of those. We just have secant theta d theta. Anyone know what type of integration this would be? I think you can maybe do it with integration by parts. I can't remember. There's a proof for it. If you look online somewhere, there's a proof for it somewhere online. But this is a yellow sheet problem. So on your yellow sheet, if you look, it will tell you that the integral of secant is 1/2 ln of secant plus tan. So I wouldn't expect you guys to get that by hand. So this is the answer in terms of theta. So what do we do now to get the answer in terms of x? Draw the triangle. So we have secant is hypotenuse over adjacent. And then we have tan is opposite over adjacent. So if we do hypotenuse over adjacent for this one, then this would be our hypotenuse. And our adjacent side would be 1. And if we do x, how do I get rid of the 1/2? Multiply it by 2. So 2x equals tan, so that means opposite over adjacent would be 2x over 1. I guess we didn't really need the triangle this time since it's just secant and tan. But you could draw it if it helps. So this would be 1/2 ln, and then what are we going to put for secant? Just the square root, right? Because it's secant, not cos. So hypotenuse over adjacent plus tan would be 2x plus c. Isn't that fun? Yes. Okay, but isn't it, stop it, Isaiah. You do your math. But isn't it kind of cool? I feel like this is kind of cool, like triangles mixed in with calculus and algebra. No, you guys are just tough crap. Okay, let's do another example. Okay, here's what we'll do. Today, we'll do 2 more examples today, and then I'll have you do one on your own, and then you can chill. So So 3 more problems today. Can we handle that? Andy, can you handle that? All right, here's the next one. All right, we've got dx over x squared plus 1 to the 3/2. What? What does 3/2 mean? It's a square root, but it's been cubed. Okay. All right, so I'm going to say this means the square root, right? X squared plus 1. Do we know which one we're using? Yeah, it's the plus 1 again. So it's going to be tan squared plus 1 equals secant squared. All right, so when I replace this one, I'm replacing my x, and what am I replacing my x with? Just tan. Okay, and so that means I've got the square root of tan squared plus 1, which is, so that's the square root of secant squared cubed. What's the square root of secant squared? Secant, so this is secant cubed, which is just secant cubed. So that means that x squared plus 1 to the 3/2 is actually secant cubed. And then what else do we have to find? Dx. So dx is secant squared d theta. Okay, so if I think about this, I don't have a plane x, but I do have a dx. And then I do have this part. So what integral do I have? So I have secant squared theta d theta over secant cubed. All right. So what's that? 1 over secant. And what is that? 1 over secant is cos. And the antiderivative of cos, sine. So we have the answer, but we have it in terms of theta. We want to have it in terms of x. So now what do I do? Draw the triangle. So we have tan is opposite over adjacent. This secant is going to be hard to get anything from because it's cubed, so I would just do the Pythagorean theorem to find the other side. So yes. Yeah, you could do that. So here you could say x squared plus 1 to the 1/2 equals secant theta. And just say the 3's canceled. Yeah. So hypotenuse over adjacent would mean that your hypotenuse is x squared plus 1. All right, so what are we going to write for our final answer? There we go. Man, that was so fun. Isn't that so fun? And he's having fun now that he's awake and stood up and stuff. Okay, last example. This one has bounds on it. I'm so excited. So, which one are we going to use this time? Secant squared minus 1, yeah. Alright, so we have x squared minus 3. So something squared minus 3. Yeah, we are going to need to be able to take out a GCF of 3 so that we can make it secant squared minus 1, which means that we need a root 3 right here so that root 3 squared gives us that 3. And then this is the one we want it to be secant squared minus 1, so I'm going to put a secant in there. So x equals square root 3 secant theta. All right, so what do we have? Perfect. So take out our GCF, we got secant squared minus 1. And then we got our tan squared. And so we have root 3 tan. So our other substitution is that x squared minus 3 equals root 3 tan theta. Okay. And then we have to know what dx is. Yeah, secant tan. So we've got root 3 secant theta tan theta d theta. Say again? We have to change our bounds. So don't write your bounds yet. We're going to have to change them and make them in terms of theta. Right? Because our bounds are in terms of x, but we're writing the entire thing in terms of theta, so we have to change our bounds so they're in terms of theta. So don't write your bounds yet, but go ahead and write your trig stuff down. Alright, so for us to change our bounds so that they're in terms of theta instead of in terms of x, what we need to do is we need to take this and we need to say if I plug in a specific x value, what value do I get for theta? So we want to, before we start plugging stuff in, we're going to want to isolate that theta. So I'll go ahead and divide the root 3. So I have x over root 3 equals secant theta. If we're not very comfortable with that, because it's secant, we can flip it, and then it would be cos, because secant is just hypotenuse over adjacent. So if I flip these, that would be adjacent over hypotenuse. So that's how I can make it a cos. And then theta would be cos inverse of root 3 over x. Yeah. And you'll notice our x values were positive. So what quadrants are we going to be looking in? 1 and 4, right? 1 and 4 are where they have positive values. Okay, so if we think about our two values right here, we have theta equals cos inverse of root 3 over an x value of root 3, which is cos inverse of 1. So where on the unit circle do you have an x coordinate of positive 1? At 0. So our lower bound is going to be 0. Yeah. So we said cos inverse, we plugged in our x value. This is cos inverse of 1. So we were thinking, where on the unit circle is there an x value of 1? And on the unit circle, that happens right here. And so that's a theta value of 0. So 0 degrees or 0 radians. And then for the other one, we would say cos inverse of root 3 over an x value of 2. And where would that happen? Yeah, it'd be right here. So root 3 over 2 for the x value, 1/2 for the y value. That would be at pi 6. So your theta value here is pi over 6. So that means your upper bound is pi over 6. Say it again. No, you can leave it like this. All right. So what do you guys see that cancels? Yeah, the secants and root 3s. And so what do we have then? So tan squared theta d theta. Okay. Is tan squared the derivative of something? Not quite, right? Do you guys remember, this is going to take you back. Remember when we were doing that unit and we talked about if you have different powers of trig functions, what you do with those powers? Remember we were saying like save this many, if you have an even number, save this many and replace it with this, that sort of thing. Well, there is no derivative for an even number of tans. We only like an odd number of tans. So if you don't have a derivative for that, what should you change it into? It's secant squared minus 1. You're going to replace it with the secant squared minus 1. That's a Pythagorean identity. So I know that secant squared minus 1 equals tan squared. Now, if I replace this with secant squared minus 1, why is that beneficial? Yeah, a secant squared, we do know the derivative of that, or the antiderivative of that, right? What's the antiderivative of secant squared? Tan. And then we can find the antiderivative of 1. That's pretty easy. Okay, so we're going to say we got root 3. The antiderivative of secant squared is just tan. The antiderivative of 1 is theta. And we're evaluating this from 0 to pi 6. So in this problem, we do not have to convert it back into terms of x, because we're just saying what the numerical answer is, and we're able to do that since we converted our bounds into radians. We can do that without converting it back. So I'm just going to say root 3 times tan of pi 6 minus pi 6 minus tan 0 minus 0. So that's nothing. Tan of 0 is 0. Okay. So now I've got a picture. Tan of pi 6 would be what? Y divided by x. it'd be 1 over root 3. So we've got a root 3 times 1 over root 3 minus pi over 6. And we can just distribute. Or we can say this is an FRQ so I don't have to keep going. So root 3 over root 3 is just 1 minus root 3 pi over 6. Well, that's fun. Wasn't that enjoyable? Don't you feel like your brain like grew so much today? Yeah, they are kind of tricky, aren't they? But aren't they kind of cool too? Would you think they were more cool if you weren't so burnt out right now? Like if you learned this months ago, it'd be like, oh, that's cool. All right, we're gonna do 1. I will put it up on the screen. We're gonna do 1, and then you're gonna take a break for the rest of the day. Okay, so the problem that you are doing this is, I'm just writing this for reference for when we start to do some more of them. Page 539, I'm just going to have you do 21 right now. And 21 says the integral of 1 over the square root of 16 minus x squared dx. So you do that one, and then you're done.